According to the National Electrical Code, the grounded or neutral conductor and the grounding electrode conductor or ground must be routed to the panel where the overcurrent protective device is located. In a scenario with multiple panels, it's essential to understand how to properly connect the neutral and ground wires. Let's break down the specific situation. Imagine you have a double panel setup with circuits numbered 1 through 42 on the left side and 43 through 84 on the right side. Circuit 34 originates from the right panel, and you need to connect its ungrounded conductor to the appropriate breaker, potentially requiring it to pass through a nipple to reach the left panel. The question then becomes whether the neutral and ground conductors associated with circuit 34 must also be routed to the left panel, or if they can remain in the right panel where they originate. The code dictates that since circuit 34 is supplied by a breaker located in the right panel, the corresponding neutral and ground conductors must be terminated on the neutral and grounding bars within that same right panel. Routing the neutral and ground conductors through the nipple to the left panel and then back to the right panel would violate the NEC. This is because it introduces an unnecessary increase in the length of these conductors. Increasing the length of the neutral and ground conductors can have several negative consequences. Firstly, it can increase the voltage drop on the circuit. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to malfunction, operate inefficiently, or even fail prematurely. Secondly, unnecessarily long neutral and ground conductors can create a potential safety hazard. The ground conductor is intended to provide a low impedance path for fault current to return to the source, allowing the overcurrent protected device, such as a circuit breaker or fuse, to trip and to energize the circuit in the event of a fault. If the ground conductor is too long, its impedance will increase, reducing the amount of fault current that flows and potentially preventing the overcurrent protective device from tripping quickly enough to prevent damage or injury. It's crucial to ensure that all electrical work complies with the NEC to ensure safety and prevent electrical hazards. To further elaborate, let's discuss the specific requirements for grounding and bonding in electrical systems. Grounding refers to connecting the electrical system to the earth, while bonding refers to connecting different conductive parts of the electrical system together to create an electrically conductive path. The purpose of grounding is to provide a reference point for the electrical system and to limit the voltage in the system in the event of a fault. The purpose of bonding is to ensure that all conductive parts of the electrical system are at the same potential, which helps to prevent electric shock hazards. The NEC contains detailed requirements for grounding and bonding, which are designed to ensure the safety and reliability of electrical systems. Some of the key requirements include the following. 1. The grounding electrode system must be connected to the earth through a grounding electrode, such as a ground rod or a metal water pipe. 2. The grounding electrode conductor must be sized according to the size of the service entrance conductors. 3. The neutral conductor must be grounded at the service entrance. 4. All metal enclosures, such as electrical panels and junction boxes, must be bonded together. 5. All equipment grounding conductors must be connected to the grounding bus in the electrical panel. 6. All branch circuits must have an equipment grounding conductor. It is important to note that the NEC is a minimum standard and local jurisdictions may have additional requirements. It is always best to consult with a qualified electrician to ensure that all electrical work complies with the applicable codes and regulations. Now let's consider some additional factors that may affect the routing of neutral and ground conductors in multiple panel systems. One factor is the size of the conductors. The size of the neutral and ground conductors must be sufficient to carry the expected fault current. If the conductors are too small, they may overheat and cause a fire. Another factor is the type of insulation on the conductors. The insulation on the conductors must be rated for the voltage and temperature of the circuit. If the insulation is not rated for the application, it may break down and cause a short circuit. Another factor is the method of installation. The conductors must be installed in accordance with the NEC requirements. If the conductors are not properly installed, they may be damaged or create a safety hazard. When working with electrical systems, it is always important to take precautions to prevent electrical shock. Some of the precautions that should be taken include the following. 1. Always turn off the power before working on any electrical equipment. 2. Use insulated tools. 3. Wear rubber gloves and safety glasses. 4. Never work on electrical equipment when you are wet or standing in water. 5. If you are not qualified to work on electrical equipment, call a qualified electrician. In summary, the neutral and ground conductors for circuit 34 must be terminated and the neutral and grounding bars in the right panel where the breaker for circuit 34 is located. Routing these conductors through the left panel and then back to the right panel would violate the NEC and create a potential safety hazard. Always consult the NEC and a qualified electrician for specific guidance on electrical installations. Let's delve deeper into the practical implications and considerations of grounding and bonding in electrical systems, particularly in the context of multiple panel configurations. Consider a scenario where you have two panels, Panel A and Panel B, fed from a common service entrance. Panel A serves a set of loads, and Panel B serves another set of loads. Each panel has its own neutral busbar and ground busbar. The neutral busbar is bonded to the panel enclosure and connected to the grounding electrode system at the service entrance. The ground busbar is also bonded to the panel enclosure and connected to the grounding electrode system. Now, let's say you have a circuit that originates in Panel A and feeds a load in Panel B. The ungrounded conductor for the circuit would be routed from the breaker in Panel A to the load in Panel B. The neutral conductor would be routed from the neutral busbar in Panel A to the load in Panel B. The equipment grounding conductor would be routed from the ground busbar in Panel A to the load in Panel B. It is important to note that the equipment grounding conductor must be sized according to the overcurrent protective device protecting the circuit. In this example, the equipment grounding conductor would be sized according to the breaker in Panel A. Now, let's consider a scenario where you have a fault in the circuit that feeds the load in Panel B. The fault current would flow from the ungrounded conductor to the equipment grounding conductor. The equipment grounding conductor would carry the fault current back to the ground busbar in Panel A. The ground busbar in Panel A is bonded to the panel enclosure and connected to the grounding electrode system. This allows the fault current to flow back to the source, which will cause the overcurrent protective device, such as the circuit breaker or fuse, to trip and de-energize the circuit. It is important to ensure that the equipment grounding conductor is properly sized and installed to provide a low impedance path for fault current to flow. If the equipment grounding conductor is not properly sized or installed, it may not be able to carry the fault current back to the source quickly enough, which could result in a dangerous voltage on the equipment and increase the risk of electric shock. In addition to the equipment grounding conductor, it is also important to ensure that all metal enclosures, such as electrical panels and junction boxes, are properly bonded together. Bonding helps to ensure that all conductive parts of the electrical system are at the same potential, which reduces the risk of electric shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal enclosures together. The bonding jumpers must be sized according to the size of the conductors that are installed in the enclosures. It is also important to ensure that the bonding jumpers are properly installed and tightened to provide a good electrical connection. Another important consideration is the use of ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect people from electric shock by monitoring the current flowing in a circuit. If the GFCI detects a difference in current between the ungrounded conductor and the neutral conductor, it will trip and de-energize the circuit. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a higher risk of electric shock. In addition to GFCIs, it is also important to use arc fault circuit interrupters, or FSIs. FSIs are designed to protect against electrical fires by monitoring the current flowing in a circuit. If the FSI detects an arc fault, which is a dangerous electrical discharge, it will trip and energize the circuit. FSIs are required in certain locations, such as bedrooms, where there is a higher risk of electrical fires. When working with electrical systems, it is always important to follow all safety precautions. Some of the safety precautions that should be followed include the following. 1. Always turn off the power before working on any electrical equipment. 2. Use insulated tools. 3. Wear rubber gloves and safety glasses. 4. Never work on electrical equipment when you are wet or standing in water. 5. If you are not qualified to work on electrical equipment, call a qualified electrician. In conclusion, proper grounding and bonding are essential for the safety and reliability of electrical systems. When working with multiple panel configurations, it is important to ensure that the neutral and ground conductors are properly routed and terminated. It is also important to ensure that all metal enclosures are properly bonded together. Finally, it is important to use GFCIs enough size in the appropriate locations to protect against electric shock and electrical fires. Understanding the underlying principles and practical applications of these concepts is crucial for anyone working with electrical systems. The National Electrical Code provides the guidelines for safe and effective electrical installations, and adhering to these guidelines is paramount. Remember, electrical work can be dangerous, and it is always best to consult with a qualified electrician if you have any questions or concerns. Let's further explore the nuances of grounding and bonding in complex electrical systems, particularly those involving multiple panels and various types of equipment. Consider a situation where you have a building with the main service entrance and several subpanels located throughout the building. Each subpanel serves a different area or type of load. The main service entrance has a grounding electrode system that is connected to the earth. Each subpanel also has a grounding electrode conductor that is connected to the grounding electrode system at the main service entrance. This creates a common grounding system for the entire building. Now, let's say you have a piece of equipment that is powered from one of the subpanels. The equipment has a metal enclosure that needs to be grounded. The equipment grounding conductor is routed from the equipment to the ground busbar in the subpanel. The ground busbar in the subpanel is connected to the grounding electrode conductor, which is connected to the grounding electrode system at the main service entrance. This provides a low impedance path for fault current to flow back to the source in the event of a fault. It is important to ensure that the equipment grounding conductor is properly sized and installed to provide a low impedance path for fault current to flow. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit that feeds the equipment. It is also important to ensure that the equipment grounding conductor is properly connected to the equipment and to the ground busbar in the subpanel. In addition to the equipment grounding conductor, it is also important to ensure that all metal enclosures, such as electrical panels, junction boxes, and equipment enclosures, are properly bonded together. Bonding helps to ensure that all conductive parts of the electrical system are at the same potential, which reduces the risk of electric shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect the metal enclosures together. The bonding jumpers must be sized according to the size of the conductors that are installed in the enclosures. It is also important to ensure that the bonding jumpers are properly installed and tightened to provide a good electrical connection. Another important consideration is the use of isolated ground receptacles. Isolated ground receptacles are designed to reduce electrical noise and interference in sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is not connected to the metal enclosure of the receptacle. The separate grounding conductor is connected directly to the grounding electrode system at the main service entrance. This helps to isolate the sensitive electronic equipment from electrical noise and interference that may be present in the building's grounding system. Isolated ground receptacles are typically used in applications such as computer rooms, recording studios, and medical facilities. When working with electrical systems, it is always important to follow all safety precautions. Some of the safety precautions that should be followed include the following: 1. Always turn off the power before working on any electrical equipment. 2. Use insulated tools. 3. Wear rubber gloves and safety glasses. 4. Never work on electrical equipment when you are wet or standing in water. 5. If you are not qualified to work on electrical equipment, call a qualified electrician. In conclusion, proper grounding and bonding are essential for the safety and reliability of electrical systems. When working with complex electrical systems, it is important to ensure that the grounding electrode system is properly installed and maintained. It is also important to ensure that all equipment grounding conductors and bonding jumpers are properly sized and installed. Finally, it is important to use isolated ground receptacles in the appropriate applications to reduce electrical noise and interference. Understanding the principles of grounding and bonding and following all safety precautions will help to ensure a safe and reliable electrical system. Let's explore grounding and bonding in specialized applications, such as those involving sensitive electronic equipment or hazardous locations. In applications involving sensitive electronic equipment, such as computers, audio equipment, and medical devices, it is crucial to minimize electrical noise and interference. Electrical noise can disrupt the operation of these devices and cause them to malfunction. One way to minimize electrical noise is to use a dedicated grounding system for the sensitive equipment. A dedicated grounding system is a separate grounding system that is isolated from the building's main grounding system. The dedicated grounding system is connected directly to the grounding electrode system at the service entrance. This helps to isolate the sensitive equipment from electrical noise and interference that may be present in the building's grounding system. Another way to minimize electrical noise is to use shielded cables. Shielded cables have a conductive shield that surrounds the conductors. The shield is connected to ground and helps to block electrical noise from entering the cable. Shielded cables are typically used for data and communication cables. In hazardous locations, such as areas where flammable gases or vapors are present, it is crucial to prevent explosions. The electrical equipment used in hazardous locations must be designed and installed to prevent ignition of the flammable gases or vapors. One way to prevent explosions is to use explosion-proof equipment. Explosion-proof equipment is designed to contain any explosion that may occur inside the equipment. The enclosure of the equipment is strong enough to withstand the pressure of an explosion, and the joints and seams are sealed to prevent the escape of flammable gases or vapors. Another way to prevent explosions is to use intrinsically safe equipment. Intrinsically safe equipment is designed to limit the amount of energy that can be released in the event of a fault. The energy is limited to a level that is below the ignition energy of the flammable gases or vapors. Intrinsically safe equipment is typically used for instrumentation and control circuits. In addition to using explosion-proof or intrinsically safe equipment, it is also important to follow all grounding and bonding requirements for hazardous locations. The grounding and bonding requirements for hazardous locations are more stringent than those for non-hazardous locations. This is because a spark from a faulty connection can ignite flammable gases or vapors. All metal enclosures in hazardous locations must be bonded together to provide a low impedance path for fault current to flow. The bonding jumpers must be sized according to the size of the conductors that are installed in the enclosures. It is also important to ensure that the bonding jumpers are properly installed and tightened to provide a good electrical connection. When working with electrical systems in hazardous locations, it is always important to follow all safety precautions. Some of the safety precautions that should be followed include the following: 1. Always turn off the power before working on any electrical equipment. 2. Use insulated tools. 3. Wear rubber gloves and safety glasses. 4. Never work on electrical equipment when you are wet or standing in water. 5. If you are not qualified to work on electrical equipment, call a qualified electrician. In conclusion, proper grounding and bonding are essential for the safety and reliability of electrical systems. In specialized applications, such as those involving sensitive electronic equipment or hazardous locations, it is important to take additional precautions to minimize electrical noise and prevent explosions. Understanding the principles of grounding and bonding and following all safety precautions will help to ensure a safe and reliable electrical system. The concepts of grounding and bonding are fundamental to electrical safety and proper system operation. Let's consider some common misconceptions and potential pitfalls related to these concepts. One common misconception is that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a critical role in ensuring proper equipment operation and minimizing electrical noise. Grounding provides a reference point for the electrical system, which helps to stabilize voltage levels and prevent erratic behavior. Another misconception is that any connection to earth is sufficient for grounding. A proper grounding system must have a low impedance path to earth to effectively dissipate fault current. A haphazard or poorly installed grounding system may not provide adequate protection and could even create a safety hazard. A common pitfall is neglecting to properly bond metal enclosures. Bonding ensures that all conductive parts of the electrical system are at the same potential, which reduces the risk of electric shock. Failing to bond metal enclosures can create a situation where a person could come into contact with two metal surfaces at different potentials, resulting in a shock. Another pitfall is using undersized grounding conductors. Grounding conductors must be sized according to the overcurrent protective device protecting the circuit. Using undersized grounding conductors can limit the amount of fault current that can flow, which could prevent the overcurrent protective device from tripping quickly enough to prevent damage or injury. Another pitfall is improperly installing grounding connections. Grounding connections must be clean, tight, and corrosion resistant to ensure a low impedance path for fault current to flow. Loose, corroded, or dirty grounding connections can increase the impedance of the grounding system and reduce its effectiveness. It is also important to avoid creating ground loops. A ground loop occurs when there are multiple paths to ground, which can create circulating currents and increase electrical noise. Ground loops can be avoided by using a single-point grounding system where all grounding conductors are connected to a common ground point. When troubleshooting electrical problems, it is important to check the grounding system. A faulty grounding system can cause a variety of problems such as erratic equipment behavior, electrical noise, and increased risk of electric shock. To check the grounding system, use a multimeter to measure the resistance between the ground busbar and the grounding electrode. The resistance should be low, typically less than 1 ohm. Also, visually inspect the grounding connections to ensure that they are clean, tight, and corrosion resistant. In conclusion, proper grounding and bonding are essential for the safety and reliability of electrical systems. Avoid common misconceptions and potential pitfalls by following the NEC requirements and best practices. Regularly inspect and test the grounding system to ensure that it is functioning properly. If you have any questions or concerns about grounding and bonding, consult with a qualified electrician. Let's consider the role of the authority having jurisdiction, or OJ, in enforcing the NEC and ensuring electrical safety. The AHJ is the governmental agency or individual responsible for enforcing the NEC and other electrical codes and regulations in a particular jurisdiction. The AHJ may be a state, county, city, or other local government agency. The AHJ has the authority to inspect electrical installations and to require that they comply with the NEC and other applicable codes and regulations. The AHJ also has the authority to issue permits for electrical work and to enforce penalties for violations of the codes and regulations. The AHJ plays a critical role in ensuring electrical safety by enforcing the NEC and other electrical codes and regulations. The AHJ helps to protect the public from electrical hazards by ensuring that electrical installations are safe and reliable. When planning an electrical installation, it is important to contact the AHJ to determine the applicable codes and regulations. The AHJ can provide guidance on how to comply with the codes and regulations and can answer any questions that you may have. It is also important to obtain all required permits before starting any electrical work. The AHJ will typically require an inspection of the electrical installation before it is energized. The inspection is to ensure that the installation complies with the codes and regulations. If the installation fails the inspection, the AHJ will require that the deficiencies be corrected before the installation is approved. It is important to cooperate with the AHJ and to promptly correct any deficiencies that are identified. The AHJ is working to protect the public from electrical hazards, and your cooperation is essential to ensure that the electrical installation is safe and reliable. In addition to enforcing the NEC and other electrical codes and regulations, the AHJ may also provide educational resources to the public on electrical safety. These resources may include brochures, websites, and presentations. The AHJ may also offer training courses for electricians and other electrical workers. By providing educational resources, the AHA helps to raise awareness of electrical hazards and to promote safe electrical practices. In conclusion, the AHA plays a critical role in enforcing the NEC and ensuring electrical safety. Contact the AHA when planning an electrical installation and obtain all required permits before starting any work. Cooperate with the AHA and promptly correct any deficiencies that are identified. Take advantage of the educational resources that the AHA provides to learn more about electrical safety. Understanding the role of the AHA and complying with the NEC and other electrical codes and regulations will help to ensure a safe and reliable electrical system. Let's explore the use of test equipment for verifying grounding and bonding integrity. Several types of test equipment are available to verify the integrity of grounding and bonding systems. These tools help ensure that the system provides a lower impedance path for fault current and that all metal enclosures are properly bonded together. One common type of test equipment is a ground resistance tester. A ground resistance tester is used to measure the resistance between the grounding electrode and the earth. The resistance should be low, typically less than 25 ohms. High resistance indicates a poor connection to earth, which could compromise the effectiveness of the grounding system. Another type of test equipment is a continuity tester. A continuity tester is used to verify that there is a continuous electrical path between 2 points. This is used to verify that all metal enclosures are properly bonded together. The continuity tester is connected to 2 different metal enclosures, and the tester will indicate whether there is a continuous electrical path between the 2 enclosures. High resistance indicates a poor connection, which could increase the risk of electric shock. Another type of test equipment is an impedance tester. An impedance tester is used to measure the impedance of the grounding system. Impedance is the total opposition to the flow of alternating current. A low impedance is desirable for a grounding system as it allows fault current to flow quickly and easily back to the source. A high impedance indicates a problem with the grounding system, such as a loose connection or a corroded conductor. When using test equipment, it is important to follow all safety precautions. Always turn off the power before testing any electrical equipment. Use insulated tools and wear rubber gloves and safety glasses. Never work on electrical equipment when you are wet or standing in water. If you are not qualified to use test equipment, call a qualified electrician. In addition to using test equipment, it is also important to visually inspect the grounding and bonding system. Look for loose connections, corroded conductors, and damaged equipment. If you find any problems, correct them immediately. Regular testing and inspection of the grounding and bonding system is essential to ensure that it is functioning properly. A well-maintained grounding and bonding system can help to protect people from electric shock and prevent electrical fires. In conclusion, test equipment is an important tool for verifying the integrity of grounding and bonding systems. Use ground resistance testers, continuity testers, and impedance testers to ensure that the grounding system provides a low impedance path for fault current and that all metal enclosures are properly bonded together. Follow all safety precautions when using test equipment and regularly inspect the grounding and bonding system for any problems. Understanding how to use test equipment and performing regular inspections will help to ensure a safe and reliable electrical system. Let's delve into the importance of proper documentation and record keeping for electrical systems, including grounding and bonding. Proper documentation and record keeping are essential for the safe and efficient operation of any electrical system. Documentation provides a record of the design, installation, and maintenance of the system. This information is valuable for troubleshooting problems, making repairs, and planning future modifications. For grounding and bonding systems, documentation should include the following information: the location of all grounding electrodes, the size and type of grounding conductors, the location of all bonding jumpers, the results of all ground resistance tests, the results of all continuity tests, and the dates of all inspections and maintenance. Documentation should be kept in a safe and accessible location. It should be updated whenever any changes are made to the electrical system. Proper documentation can help to prevent electrical accidents and injuries. They can also help to reduce the cost of electrical repairs. In addition to documentation, it is also important to keep accurate records of all electrical work that is performed. Records should include the date of the work, a description of the work, a name of the person who performed the work, and any materials that were used. Records should be kept in a safe and accessible location. They should be updated whenever any electrical work is performed. Proper record keeping can help to track the performance of the electrical system. It can also help to identify any potential problems before they become serious. In conclusion, proper documentation and record keeping are essential for the safe and efficient operation of any electrical system, including grounding and bonding. Documentation provides a record of the design, installation, and maintenance of the system. Records provide a history of all electrical work that has been performed. Keep documentation and records in a safe and accessible location and update them whenever any changes are made to the electrical system.